Right, we are looking at the question 397. Right, we have a spring with 4,000 Newton meters is undeformed. Right, when x equal to 0, if the body move from the initial position, it means some uh, place away, 100 millimeter, and then another 200 millimeters as the final position. So the engine problem that we have to solve here is to determine the work done by the spring on the body. And the second engine problem that we need to solve is to determine the work done on the body by its weight. So we have a chute with a 20-degree inclination angle from the horizontal um, lines. So we have three position here. The undeformed position after the body at initial state where the spring is stretched for 0.1 meters, and then we have the final state, kinematic state, where the spring is stretched for 200 0.2 millimeters. So we're going to look at the first kinematic state. In order for me to evaluate, first we would like to look at the position vector, right? Here is the origin, and if it, I'll draw here the rectangular coordinate system. The reason why I use rectangular system because later we're going to evaluate the changes of potential energy, or we want to find the work associated with the weight, or we want to know the work done by the gravitational force, right? Yeah, and then we use this arrangement so that we can formulate the coefficient matrix in order for us to convert the the position vector, which can be in s coordinate system or in uh, an t coordinate system. So the angle that we made to for conversion from S coordinate system to rectangular coordinate system is 340, and after it been deformed, right? So from this position to that position, the S coordinate will be 0.1 meters, but for in the rectangular coordinate system is 0.09 meters minus 0.03 meters in y direction. Next, we look at the second situation when we want to know the final position with respect to point O, the undeformed position, where we get the absolute force from the spring. So the angle that the x-axis made with the chute angle remain the same, 340, and the position vectors final kinematic state for the body is 0.2 meters. So we can get the position vectors expressed in s coordinate system because the body is moving in positive s direction, 0.2 meters, and we have 0.188 meters in x direction and minus 0.0684 in negative y direction. So we can combine these two position vector in order for us to determine the changes of um, the displacement of the body from when it moves from A to B, or position B relative to A, right? So this is we solve the problem using the free body diagram. We can identify the component of force acting on the body, the weight. There is a frictional force, and we have the reaction force due to the weight, and we have the spring force. So in order for us, if there is a friction, so we going to use the NT coordinate system, and from that we can find component for weight in the normal and tangential direction. So force in the tangential direction is 200 Newton for spring, right? So this one for spring, sorry. This one for force. For weight, we have the weight is about let me see again, 7 kilogram, right? And the gravitational force is 9.8 meter per second equals to 2. The angle made from this t direction with the absolute weight direction is 290, because the shoot angle is 20. So from that we can get that the component of weight that act in along a positive tangential direction, because in tangential direction as the positive direction is along the moving motion of the particles, and negative En is negative 64.46, because we define that the normal direction is towards the upward direction. And for spring, we have uh, the additional work uh, done by the spring, right? So we are using the 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 stretch from the initial state, and we get the component um, in T and N coordinate system, right? So basically, this force is directed opposing the direction of T coordinate system. So we are using negative value there, but in order for us to evaluate the conversion, right? So this one is negative x direction and positive 68.4 in y direction. Now we want to look at the um, amount of work done by the body by its weight using the work energy method, right? So we are considering the position that the body move from A to B, and we've got in S direction is 0.1 meters. So work done by the body on the body by its weight, or U, we value from 1 to 2, find the position, and this is the definition of scalar product. We can get the gravitational work by the gravitational work is 2.3 newtons, and this is the detail of the calculation. um, this one is the first position, right? The PO position, AO position, this one is BO position. And if you are using energy balance, we are looking at the change of potential energy. So we have the change of potential energy from high altitude to low altitude. We find that the value is similar to the work done on the body by its weight, so negative 2.3. and this one is the final position. This is the initial position. And then we look at the force, right? So in order for us to evaluate the force, we need this information: the position vector for B and position vector for A relative to O, right? So this is the expression of force F. We define it in terms of N and T coordinate system and in rectangular coordinate system. So work done by the spring on the force using a work energy method U12. So using the definition of scalar product, we can evaluate that the work by spring is equal to half spring stiffness, and then we have the the total spring force after the body been stretched minus at the final state, so we get minus 60 Newton meters. And from here we can evaluate the work by spring. So there is a two method here just to demonstrate that it is possible to doing it because the force is constant in t direction and in x and y direction. So we are using based on S coordinate system. This one based on component of force described in x and y direction. So we have negative 60.05 because this one the effect of the truncating the solutions. And then we are looking at the work done by the particles to stretch the work spring, which is work out. We have half k. This is the length of the spring when it reaches to final state. This is the differences of the work done by the particle at the initial state. So again, we are using the same approach. We are looking at the S coordinate system. We are looking at the XY based on component of coordinate system. We still get the same values that work out. The work done by the particle to stretch the spring, which is work done by the body to the thermodynamic system to the surroundings, about 60.05 meters.